Okay, so we're going to do the next part, and it says, in 2011, a tsunami hit the island and killed off 90% of snail populations at all levels. Okay, so everybody is going to remove all but 10 beads in their populations, all right? And then they're going to record their frequency. Now, they don't have to, it says to simulate this, they're going to gather 10 identical beads to repopulate. Don't have them do that. It's an epic waste of time, okay? So they can pretend, I mean, they can do the math. What's it actually going to be, okay? So just have them do the math. And so after the tsunami, can I spell tsunami? So after the tsunami, what would their populations be if they were to rebound from the 5 individuals that they chose, the 10 beads? And this is where you're going to see their numbers all over the map, right? You might have this drop down to 20% yellow. You might have 100% yellow. You might have 50% yellow, all right? They're going to be all over the map. Same thing here. Same thing here and same thing here. You're going to have numbers that are all over the place. So then you're going to ask them, so what happened? How did we get, what made it change? Well, and they should be able to say that, well, we randomly chose 10 and it may not have been representative of the population. And that's exactly right. When you go down to a small population size, the survivors aren't always representative of the population that it used to be. And so that's going to cause change that has nothing to do with how fit they are. It has nothing to do with people coming in and out. There's no purpose to it. It is just random drift of the frequencies because of a small population size. And we call that genetic drift. So if you want to stay in Hardy-Weinberg and not change, you can't have genetic drift happen. So no genetic drift. And there's 2 ways that genetic drift often occurs. Okay, genetic drift can occur just by random, just in our populations, one allele will fixate or become more common. But no genetic drift, 2 ways that this can happen. One is bottleneck. And that's what we just saw. So a bottleneck is when you take the large population and they all bottleneck into a tiny population. And a good example of that is the cheetah population. It's been bottlenecked, and so they're very inbred, and there's really lots of differences in their genetics. And the other way is the founder effect. Okay, and the founder effect is, it's like a bottleneck. So a bottleneck, you take this large population, right? You take this big population and you kill off everybody but these guys. They're all dead. Okay? In a founder effect, these guys just leave and start their own population. It's the same idea, but we're going down to a small population size. So a good example of the founder effect is the Amish, who have a lot of polydactyly in their population. Or the polygamists down in Colorado City and Hilldale that have a ton of fumaric aciduria. It's a disease. Because of the founder effect. They just so happen to be an unequal representation of the general population, and they carry a high frequency of 1 or 2 alleles that aren't normally there. Okay? All right, so that's that one. Then the very last one that they're going to do, 7, 8, it says, all right, so let's say that this population of snails actually lives on a beach close to Fukushima, Japan, okay, where we had the tsunami and then the earthquake and the nuclear reactor melted down, okay? Oh, you're not going to tell them that, though. Following a massive earthquake. So the scientists return in 2021, and they find these proportions. So what they find is same thing in the high and the mid. We've got 90 and 85, and in the low is 5. But in the low populations, you have a new allele and a couple in the mid. A brand new one. It's like we have yellow beads, white beads, and then we have a green bead. So all of a sudden they have 25 green beads in there. What is going on? 25% of the population has this green allele. Excuse me. So they're going to try to come up with hypotheses for why you have this green allele. And let them see if they can figure it out. Have them Google what happened in Fukushima. Why might that have done something? Have them look it up. Well, it turns out, don't tell them this, but they'll figure it out, that when the nuclear reactor melted down, the Japanese took seawater, and they cooled the reactor with seawater, and then they just allowed the water to rush back into the sea with all of the nuclear waste. And so it caused mutations in the wildlife that were there. Now, these particular snails were not there. This is sort of part of our scenario. But it would have done the same thing to these snails. You would have different alleles, mutations. So that's the key, right? If you don't want any changes, what can't you have? You cannot have mutation. Oh, whoops, it should say no mutation. Okay, so you cannot have mutation. Because if you do, it's going to change the allele frequencies. Okay? So then at the end, you want to tie it back together and say, all right, so in order to stay in Hardy-Weinberg, in order to not evolve, you have to have totally random mating. You have to have no environmental change. You have to have no gene flow of any kind, no natural selection, no genetic drift, and no mutations. How often does that occur in nature? Never. Think about the human population. So this is a really good one to sort of introduce human evolution. Did humans evolve? Well, if they didn't, we had to meet all of these assumptions. Does the human population meet all these assumptions? Absolutely not. None of us meet all of these assumptions. Everyone is evolving because no one can meet these assumptions. So then that begs the question, what the heck? Why do we even have the Hardy-Weinberg equation? If it never works and it never fits a real population, what is the point? And that is important. The point is, it is our null hypothesis. If you're familiar with statistics, the null hypothesis says nothing happened, nothing worked, there was no effect, nothing's changed. Okay, that's our null hypothesis. That's what the Hardy-Weinberg equation gives us. Okay? So if you're trying to figure out if there is natural selection going on in a population, then what you would do is sample a population, based on the phenotypes you see, figure out what the allele frequencies are, and then predict how much of this disease, for instance, you should see in the population. But if you don't see that in the population, then something is causing it to be out of Hardy-Weinberg equilibrium, and your hypothesis is natural selection. This is your control. It's your control group. It's your baseline. This is what should occur if no evolution is happening. But if you see that your population does not fit this model, then you can start making hypotheses about, well, maybe there's non-random mating going on. Maybe the environment has changed. Maybe there's some gene flow. Maybe there's natural selection or genetic drift, or maybe there's been a mutation. So these are hypotheses that you can test once you see that your population does not fit the null, does not fit the baseline or the control. Okay? So that's the purpose of Hardy-Weinberg equation. All right, so the homework is going to have them practice some of those. So I'm going to pause this and go through the homework.